Hello everyone, welcome to the webinar for density measurement in mineral processing. We'll just wait a few more minutes for people to come and join. In the meantime, familiarize yourself with the GoToWebinar interface. So if you can see on the process map over here and in front of you, the GoToWebinar interface, you can see that on the right hand side there's some handouts that I've attached, and I'll talk about them a bit later as we go through the webinar. And you can also increase or decrease your webcam window over there in the window. And of course, throughout the webinar, you can also type in your questions on the right hand side in the chat, and I'll get to your questions at the end. A bit about myself just before we start the webinar. My name is Taylor McCurditch, and I'm the industry manager for mining and metals and oil and gas here at Endress+Hauser, Australia. I'm based in the Sydney office, which is where the head office is, and we have a team of sales engineers and product experts as well in Australia that can help you with any of your applications. In general, I think a lot of you already know about Endress+Hauser and what we offer in terms of products. But you can see here on this slide that there is a large range of products that we do offer, from level, flow, liquid analysis, gas analysis, pressure, density, temperature, and then all the system components and products that help bring the information from the process field into the cloud or into your SCADA control system. We also offer services as well, whether it be commissioning or maintenance or repair of the instrumentation, whether it's our own devices or if it's third-party devices. So we would consider ourselves a full service provider and also a full MIV or a main instrumentation vendor for any projects that you might have. So I'll jump straight into what we're going to be covering over the next half an hour to 40 minutes or so. What I want to do is I'll go through each of the 4 different technologies. So radiometric, Coriolis, vibronic fork, and differential pressure. And once I go through all those 4 technologies and discuss how they're used in density measurement for slurries and mining, then I'll finish off with any questions. So again, for some of you that joined a bit later, if you want to enter your questions into the chat on the right hand side, then I'll get to them. And I also want to thank those who submitted questions as well earlier in the registration process. So I've crafted this online seminar a bit around those questions. The first measuring principle that we're going to be speaking about today is around radiometric, and it's probably the one that you familiarize yourself the most around measuring slurries in mining applications. I'll go through very briefly around why we use nucleonic measurement for measuring density in slurries as like a default, or is one of the most common methods that you see in mineral processing. And the reason why is that nucleonic measurement is very reliable when other measurement principles fail because of different or extreme process conditions. And those experienced in mining processing plants are very likely to be either harsh or abrasive, or what we would consider as an extreme process condition. Things like heavy abrasion or corrosion, high temperatures or pressures, or it's just something around the design of the installation of the vessel or the pipe that you're using. The radiometric measuring system is one that's very common in Australia. So a bit of an overview around the radiometric measurement system It's a non-contact measurement and non-invasive. So that means those two components there that you see on the right-hand side, both the yellow container, which is the source container, and then the blue and the stainless steel detector on the right-hand side, they're fitted externally, and we'll see some applications in a moment. And they're used for level measurement, point level measurement, interface measurement, but the fourth type of application that they're normally used for is density measurement, and that's what I'll be speaking about in today's seminar. So I spoke about our extensive portfolio that we have in Endress+Hauser, and alone in the radiometric area, we have a really extensive portfolio that will fit a lot of applications out there. So with the system of radiometric measuring principle, you require a source, so that creates the radiometric waves. That source needs to be stored in a source container, and we have different containers depending on the strength of the source and the shielding capability. Then you need a detector to detect the radiometric waves on the other side. We have two detectors available right now. The FMG60, which is the 4-wire device, which is the older one, which a lot of you are familiar with. And then there's the world's first 2-wire loop powered device, which is the FMG50. And that comes with additional features such as Bluetooth connectivity, has a higher temperature limit, has self-verification technology called heartbeat technology, and it's still as well. And then we have other accessories such as modulator, just in case you have radioactive material in your processing. And we also have a pneumatic container. So this meets the Australian standards for source containers. And what that means is you can automatically interlock that pneumatic container with your pump, for example, so that when there's no material flowing through your pipe, you can automatically shut off the source, and that prevents blinding of the detector and improves your reliability of your measurement. In density measurement configurations, you can see that there's a number of different ways that you can configure the device to ensure that you have a reliable measurement. The first one is around vertical pipes, and that's around the most constant conditions. So a lot of coal mining or coal processing plants in Australia use this radiometric principle on vertical pipes. There's also different configurations that we can use, like we can have a longer beam path if we want additional accuracy or a larger measuring effect. So that detector that's on a diagonal there, that means there's more of the slurry that attenuates the signal, so we can get a better reading with the detector. We can also have an S-bend arrangement, which can also increase the measuring path of the beam path as well, which can assist in accuracy of the measurement. And then finally, there's a horizontal pipe arrangement. So we only recommend this if only horizontal pipes are available. And we ensure that the source container and detector are in the middle of the pipe, so that you don't measure any buildup that might be at the bottom of the pipe, or detect any air bubbles that might be at the top. So the configuration of the source container and the detector, it really depends on the measuring range, the measuring effect, what we want to achieve, the pipe material, the diameter of the pipe as well, and maybe the conditions too. So it all depends. So if you want to learn more about that, we can definitely discuss it in depth. I'm going to go through two examples now around radiometric density in different applications. So this one is a 2-inch pipe, which you might traditionally think is a bit difficult to utilize a radiometric measuring principle in. This happens to be a copper slurry. And because it's a 2-inch pipe, we use the S-bend configuration, where you have a longer measuring path between the source container and the detector. So the benefit of this is, of course, the whole system is very reliable, has a sodium iodide detector crystal in here, which is very stable reading, has a local display and Bluetooth capability as well for the 2-wire device. And that's great for the process engineers and the maintenance staff that don't have to go all the way up to the source container or the detector to configure the device. And it makes it much safer and much easier as well. Okay, so now I'm going to the other side and having a very large pipe. This is a DN 900 pipe, again of copper slurry. The pipe wall here has 20 millimeters of rubber as well on the side, and that means a much bigger source and source container required, and detector as well. So you can see there the bit of the difference. The detector is on one side of the pipe and the source container is on the other. So this one here was a much bigger source, a 2000 millicurie source, and it's using the FMG 60 as well. So you can see the two different configurations, whether you've got a small pipe or a large pipe, there's a different solution depending on what the conditions are that you have in your processing plant. Now, a lot of questions that we get is around how accurate is this system, and I'll talk about the accuracy of all the systems, but around the radiometric principle, so accuracy really depends on each application. So it's dependent on the pipe diameter, the density range of the process, the source activity, how old the source is, the sensor material of the detector, whether it's sodium iodide or PVT, and that also depends on the stability of the detector, the dampening time, and the calibration as well. And as a general rule of thumb, in terms of the approximate achievable accuracy, so with a large pipe diameter, with a sodium iodide crystal, you can get around 3 to 5 grams per liter accuracy. And then as you go up in diameter, so above that, the 8-inch to a 20-inch, so DN 500 line, your accuracy improves, so it goes down to less than 2 grams per liter. And 2 grams per liter is an SG of 0.002. So you're getting into very good accuracies, and this is why the radiometric principle is used a lot in controls loops in processing plants across Australia. So that was the radiometric principle. If you want more further information, I did do a webinar last year about a lot more in depth around the radiometric measuring principle and how it works as well. So if you want to check that out on our website, you definitely can. Or you can shoot me a question later and I can send you the link. I'm going to go into the next measuring principle here, which is the vibronic fork. And I'll explain how the vibronic fork works in density measurements. So it's what we call the liquefant, and that's as a technology that Endress+Hauser have been, I mean, it's got a very long life with Endress+Hauser. I think in the 1970s it was first sold here. So about 50 years the device has been in different generations. And the measuring principle of the vibronic fork is the vibronic fork has a resonance frequency. And this resonance frequency changes as the moving mass changes of those forks. So if the density of the material that the forks is vibrating in changes, then that resonance frequency will change. But it's also important to note here that because the dampening effect of that resonance frequency changes depending on a lot of other constants as well, such as the process temperature, as you can see here in this graph, as the different color lines which indicate different temperatures change, that resonance frequency also changes. The process pressure can also affect it, because if you have to think about it, as the process pressure increases, the dampening effect also increases as the forks can't move as well. And then if the forks were to reduce mass by abrasion or increase mass by buildup, that can also affect the measurement. So that's why internally in the devices that we sell, the liquefants, it also has heartbeat technology, which can identify when there's abrasion or buildup of the vibronic fork and send an alert so that you can either maintain the device or inspect and replace if required. And the good thing is that it's very easy to also calibrate. So as long as the device is continually calibrated, because this is a contact device, which means it's in contact with the measurement. So you can imagine a slurry would abrade the device. And depending on what type of the slurry it is, we can offer different materials to maximize the longevity of it. I think some of you might also be asking the question, how long it would last in different processes, and I'll go through some specific examples in a minute. But that equation there down the bottom is a relationship of density using the vibronic fork. So where S and F0 are their sensor constants, but you can see there that temperature and pressure are dependent as well in the equation. So they're important factors for us to consider when installing a application such as this. And what applications have we got liquefans installed in? So we have gravimetric separators, some like separation boxes, overflow of cyclones, distributors to cyclones, underflows of thickeners or tanks or filtration areas, pipelines or tailings pipes. So it's really where we've got small particle size, the slurry is very homogeneous. There's no large entrained air bubbles or gaps in the process, and that will give us a great accurate measurement. One of the first examples I'll go through is in a cyclone underflow application. So this is an iron ore example where the particle size D50 is a 0.5 mil. We've got a 14-inch carbon steel line here, and the velocity of this slurry here is very high, so 3 meters per second, and the deviation is plus or minus 2 meters a second there. And that, because it's a contact measurement, I put the operation lifetime there of 7 months. Now there's different ways to mitigate this, and I can go into a bit further detail as we go along in the seminar. But as abrasion is really related to the particle size, the abrasivity of the slurry as well, and the velocity of the slurry, you can see here that the particle size was relatively large, and the velocity is quite large as well. That's why the device only lasted 7 months in this application. The fork here was just metal, so it wasn't coated or anything, so that also would have, if it was, then it would have extended lifetime here. Another example is around flotation feed. So this is an iron ore slurry again, but the particle size is much less, so 0.15 millimeters. And the velocity here, because it's in a tank, is much smaller as well. So the operation time of the device here was more than 1.5 years. You can see where the device was installed into the tank. And that's just another example where the liquefant worked quite well. I'll give you another example now. This is around the filtrate of a belt filter. So the particle size here is also very small, 0.1 mil, and the operation time of this device was also 18 months plus. And you can see the density there. It was another iron ore application. And finally, the final example I have for the liquefant is tailings lines applications. So this is again on iron ore tailings. I tried to keep the same commodity to standardize the comparison between the different particle size and the velocity and the operational lifetime. So this here, the particle size was 0.1 mil. This is a 16-inch line, and you can see on the picture there, the speed of the slurry was quite high, but the site mitigated that by having the vibronic fork in a spigot piece here. As you can see here, it sticks out. And the operation time of the device here was 1.5 years. This one also had pressure and temperature compensation. And what I'm going to do now is I'm going to explain the different configurations. So as you can see on the left-hand side, this is the application that you just saw in the tailings line. So there was a pressure sensor on the tailings line. The output of that went into the density computer, which we call the FML621. We also had temperature compensation, so there was a temperature device in that spigot that was input also into the density computer. And then the liquefant, so that resonance frequency output was also being put into the computer. So that computer then calculated from the pressure, the temperature, and the resonance frequency there, the correct density. And then on site, they just use that as digital comms to get through the Profibus onto their site. There's other ways also that we can utilize to install in a pipeline. So the right-hand side shows another example where it was just temperature compensated with a liquefant, and that was also in a different spool. The sensor was offset as you can see from the tailings line there. So you can get that liquefiant from a 45-degree angle into the center of the flow to give you the best accuracy. And again, that goes into the FML621 density computer, and then there's either an analog output if you want, or it can be a digital communication output as well. And you can get some additional information there from those other devices that are feeding into the density computer. And another one of you asked questions as well around comparing the liquefiant with the radiometric system, so the system that we saw before. And here's an example from a site where we compare the liquefiant and the gamma, or the radiometric measurement. And you can see here that the difference was very small. And we've seen a correlation with 0.02 grams per centimeter cubed in this application. So within 0.02, and the customer was very happy with that. So in areas where you don't necessarily need that super high accuracy for control, or you're happy to have a contact measurement where you have to calibrate it every so often to compensate for that wear of the probe, then this would be a good example. So maybe a tailings line, you might have a requirement for monitoring of density, or some other type of process as well. So I'm going to move on to the third different type of technology here for measuring density in slurries, and that's the Coriolis meter. So Endress+Hauser have got a lot of experience in different Coriolis measurements. Initially, they weren't designed with thinking of measuring slurries in, but these days we do use Coriolis meters in mining for lots of different applications now. So whether it's slurries, or whether it's fuels, or whether it's gases as well, so whether it being like compressed air, natural gas for burners, oxygen for dosing into leaching areas, whether it's lube oils, chemical dosing, frother dosing, collectors, flock or tailings densities, or thickening densities. Here's a number of pictures of lots of different applications of Coriolis meters installed either in slurries, liquids, or gases. So that picture on the right hand side is lube oil viscosity measurement using this ProMass I300 that I'll talk about on the next slide, and that can measure viscosity as well as flow and density. So it's a good indication of the quality of the lube oil in the mill. And then you've got another example of a slurry measurement on that top left-hand side there. And I'll show you shortly about that example. But the Coriolis meter I just want to describe to you today that is best suited for slurry applications is called the ProMass I. And the reason why is because that has a single straight tube design with titanium measuring tubes, and it's quite good for slurries. So it also has a full bore option. So that means that the size, the ID of the pipe will be the same inside the meter as well. So there's no step in or step out. That means that there won't be any localized wear inside the meter itself. So we find that it really has great longevity and life, because obviously with any contact measurement, you're going to have some type of abrasion with a slurry in there. But as I mentioned before, abrasion of the device does depend a lot on the particle size, the type of particle, the shape, and also the velocity. So if those things are considered when we're designing a solution involving a Coriolis meter, then you'll have no problem measuring. And I'll show you an example now where we installed a Coriolis meter this is in a correct medium application for a coal processing plant, so where it enters the cyclone feed sump. And that measuring point was used for control. So normally radiometric is used for control as well, and we just compared the Coriolis meter to a radiometric measuring principle. The ProMass I300 itself has a measuring density down to 0.0005 grams per cubic centimeter, so more accurate than the liquefiant. And this application here was using a straight tube full bore meter designed to reduce abrasion. In the event that you have a large line, so it would be impractical to utilize a Coriolis meter for full bore arrangement for, like, let's say, for a DN400 or a DN600. In fact, the largest full bore size meter we have is a DN50. But to minimize any cost and complexity, you can utilize a bypass arrangement like shown on the slide. So you just need to make sure that you use abrasion-resistant ball or gate valves for the isolation purpose to minimize any pressure loss in the bypass system. And the flow going through the Coriolis meter can be adjusted by an orifice plate and the downstream bypass valve as well. It's important to keep like a water supply hose fitting up the top of that line as well, just in case something gets stuck in there, some tramp material or something in the process, you can flush it out. And then there's another valve out there down the bottom for a drain or back to the sump or something like that. If there's any other arrangement as well that you want to utilize to ensure that there's a representative material going through that Coriolis, then that can also work here. But we find that this bypass arrangement for those large line sizes is the most common. Here's another example where we utilize Coriolis meters in a nickel slurry. So this one, because the slurry wasn't too abrasive, in fact, the particle size was really, really small and the velocity wasn't too high. So we could use the bent tube Coriolis meter. And the way we installed it, you can see in the picture there, is on a vertical aspect as well. This was here to control the mass flow rate to the roaster and also the feed density to the roaster as well. So you can see that can be used in lots of different applications with slurries as well. We had some more questions also around, okay, so you have these Coriolis meters and there's a slurry application, but the question's always asked around, the slurry will degrade the meter, won't it? How do we know that there's going to be no holes in the meter, or the performance or the accuracy isn't decreased because of this abrasion? And the great thing is that our Coriolis meters come with heartbeat technology. And for those that might be familiar with heartbeat technology, it's around the self-verification software, which means it monitors the health of the instrument. It doesn't just monitor the health of the electronics, but also the sensor body itself. So it can determine if there's corrosion or abrasion in the tube itself, whether it's buildup, whether there's air entrainment, whether there's cavitation or bubbles or anything else like that. And that's really good when measuring these devices in a slurry application. And you can also perform a lot of predictive maintenance on it. So there's a secondary variable called HBSI here, and using the Coriolis meter, in this case the ProMass I300, so that straight tube one, we've done a lot of tests around this, the relationship between HBSI and the abrasion of the tube inside. So here is a graph of the HSBI over a period of time, hours, and we've got different materials. So you can see there with just water, that heartbeat sensor integrity index was stable. Once we introduced a abrasive slurry of sand, 6% here in this case, you could start to see the HSBI index going up. Then we utilized a slurry with only 3% sand. The HSBI went up as well, but not as steep. So you could indicate that the abrasion effect of the 3% sand slurry wasn't as big as the 6% sand slurry. Then we put it back to 6% sand slurry to see if the HSBI index would continue to go up at the same linear rate as it did previously, and it did. And then we reverted back to water just to make sure that the HBSI wasn't going up with any water application, and it wasn't there. So I think that's a really great example of how you can utilize this heartbeat sensor integrity index number to predict when your device is going to fail, when you need to replace it. The final measuring principle I want to cover today is around differential pressure. So Endress+Hauser have been having pressure measurement for a very long time as well, but I'm going to speak about the ceramic membrane pressure sensor now. And we offer also a metal membrane sensor, but I'm going to discuss ceramic only because really this chart here, which is the knob hardness comparison chart. And in mining, stainless steel really just doesn't cut it in terms of hardness. So you can see they're all the way down of a number of 169 for stainless steel, which is your typical pressure transmitter that you might get. But for our ceramic membrane devices, we have 99.5% pure alumina oxide membranes, which means it's very hard. In fact, it's almost as hard as tungsten carbide, which is one of the harder materials that are used in mining applications. So this is why we only recommend ceramic membrane pressure devices in this type of application. And here's an example of an alumina site where we've utilized a ceramic membrane pressure device. And you can see here that the stainless steel housing wears way faster than any ceramic one. So when we use this type of device, we always make sure that the ceramic membrane is flush with the process and there's no contact with any metal, because that's just going to abrade away or wear away. In terms of a typical setup for differential pressure with a ceramic diaphragm, so here we've got what we call the PMC 71, so we've got two ceramic pressure devices here on a vertical riser or vertical pipe. Both of these outputs go into what we call an RRA46, which is a calculator here with dual input, and then you can get SG indication right there in the spot there. That calculator is really determining the density of the medium with that formula there in that box, so density times G times H. So as long as you know the height between the two different devices, then you can determine the density. So it's a very straightforward way to measure density, but in mining it's not as common these days. But we do have a few examples that I'll show later. We've recently also released a new generation of pressure devices, and with that has come an increase of accuracy. So now the device I showed, the PMC 71B, that has now an accuracy of up to 0.025%, which is the best on the market now. And that means that you can even further increase accuracy with any differential application pressure for mining as well. So here's an example. This is another coal example of utilizing a differential pressure arrangement for correct medium in coal. So this is like a tester leg arrangement where it's a bypass from the main line or main correct medium line here. And with that fixed height, you can get the differential pressure straight away on a local display. And of course, that output can go also to your SCADA system. So it's used quite effectively, and there would be a bypass arrangement in this case as well, which we can utilize using a similar bypass arrangement of that Coriolis meter that I showed earlier. So that's another great way of getting highly accurate density. So on the accuracy, we have compared the differential pressure with a radiometric solution as well. And you can see here that this is another example of where we got within 0.02 SG for this was a correct medium circuit. So differential pressure can be quite accurate depending on ensuring that it is set up correctly, and it is also a ceramic membrane diaphragm. In terms of what that was out of the box, so the dual ceramic PMC 71, just straight out of the box, is that bottom blue line. Only 2-second dampening was used, which is why the line is much more jagged, but this was straight out of the box, straight after dry calibration. And the scale, if you can see the scale, the difference between there is 0.0 0.02 SG without any correction or anything. And then further on, as the operation moved to optimize their correction, then we align the DP and the gamma very closely. So you can see here there's this variation, and the difference between dual ceramic variation and the nucleonic measuring principle here was 0.35% variation. So in summary, that was 4 different measuring techniques that you can utilize to measure density in slurry applications. So if you do have any questions now, here is your time to type in the chat box. Of course, also after leaving our seminar, there'll be like a little pop-up feedback thing that you can type in your additional questions if you want, or any feedback that you have, or you can rate our seminar as well. So make sure you do that. And then afterwards, you'll get an email from us about the slides and the link from our website that shows you all the other online seminars that we conducted over the last year. And what I might do now is I'm going to go through some of the questions and see if I can answer them. So the first question that we've got here is from Rod. He asks, can the meter health parameter be seen using an Attilian system? Okay, yep. Thanks, Rod. That's a great question. So you can bring heartbeat information or the other variables, the HSBI, heartbeat variable, into an Attilian. We can send you some further information about how to bring that a bit later. But it is an important thing, because an Attilian, for those that might not know, is around the IoT solution from Endress+Hauser. And the great thing about that is you can bring a lot of the information from the field into your cloud solution, and it can be used for monitoring or it can be used for preventative maintenance as well. That's a great question. I've got another question as well. How long does one of those liquefant density probes last in a slurry with particle size of 50 millimeters? Okay, yep, that's a good question as well. So the important thing with the liquefant is it can only measure density in a slurry that behaves homogeneously. And with a slurry particle size large, as the larger we go, the less homogeneous it behaves. Particularly in an application, and I'm not sure about your exact application, but particularly in an application where there's mixed particle size, which is typical of a large particle size like that. So the thing is that large particle sizes might bend the probe and might not really be suitable for a liquefant. Something that we see a lot more commonly for applications at that large particle size is around the radiometric principle. But if you want to add your application details afterwards, we can have a conversation about which one would be best for you. Okay, so I've got one more question. How long does the radiometric measuring principle device last in the process? Okay. So the source life itself is depending on your local requirements as well, 15 years. And depending on the local requirements as well, you'll have to make sure that you have licensing as well, and RSO, and there's a lot of fees and regulations around that too. So using a non-nuclear density source for monitoring, or one of the ones that I discussed here, is a good way to ensure that you don't have to go along that route of licensing or having an RSO or something like that. In terms of the detector, so the detector has been tested extensively around plant vibration, and you can see the results of that in the technical instructions that are added in the handout. So if you haven't checked them out now, have a look. That's in the FMG 50 technical information that are added in the handout. I also added all the other technical information as well in the handouts on the right-hand side, so you can have a look at them. And if you want any other information as well around them, just let me know. Okay, so that's all what we have time for today. I want to thank everyone for joining, and I hope you have a great rest of the day.